Good afternoon, chemists. So we're going to get started here. Plan for today, we'll do a little bit of chapter 10, maybe like 30 minutes of chapter 10, just to make sure that we cover all the content that's going to be on the final. And then we will switch to reviewing for midterm 3. And then we will also do all midterm 3 review on Wednesday. So that's like a ton of time for review, right? And I have my review session tonight. Who's going to come? Yay, all right. I'll be there. Don't use the Zoom room, all right? I have my own link and an activity for us. All right. Okay, so chapter 10, gases. So this is, we're going to go back to some math, all right? All right, so this is a big shift in what we've been talking about gases. All right, so we will, in this chapter, which remember, will be on the final, not on midterm 3. Midterm 3 is only 7 through 9. We will talk about some of the characteristics of gases and their properties based upon what changes we can make to a sample. On Friday, I plan, after the midterm, I'll do some demos that are cool that we can look at gases and see some cool things. We will do some calculations regarding gases. So this is time where we take our calculator back out, all right, take that dust off the calculator and back to calculations. And then we will go into an obscene amount of detail about gases that explains the phenomena that we see. So that's really the theme of, this, chemistry for science majors. We look at a set of observations, some type of property that we see in materials, and then go into the theory behind it. What theories explain exactly what we're seeing, kind of like all of chapter 9, right? Like all of those advanced theories of bonding. We have Lewis structures that predict one type of bonding phenomena, but then we go into like an obscene amount of detail regarding valence bond theory, MO theory, to go into those details. So it's that same kind of theme happening here. And so the behaviors we see about gases are explained by kinetic molecular theory. All right. So let's ground ourselves and think about gases, all right? Let's see if I can't kind of squish some misconceptions about gases. All right, so gases. In your brain, think about a gas. Do we think a gas is a homogeneous mixture or an inhomogeneous mixture? What do we think? Homogeneous. Great. Yeah, so homogeneous. So you might have to recall back from chapter 1 what the difference is, right, between homogeneous mixture and a inhomogeneous. Inhomogeneous means that there's like different phases present, all right? Different phases. So if we have a gas sample, all of it's the gas phase, right? So it would be a homogeneous mixture. So for example, the air that we breathe is homogeneous. It has a bunch of nitrogen, oxygen, some halogens, or not halogens, some noble gases, CO2, things like that. And they're all in the gas phase, and it's uniform in its composition, so we call it homogeneous. Oh, a trick question I love to do. Not a trick question, but it's definitely a misconception about gases is, what's a synonym for homogeneous mixture? Solution. So is air a solution? Is air a solution? Yes, it is. Yes, because we just said it's a homogeneous mixture. All homogeneous mixtures are solutions, all right? But I feel like the misconception is when we say solution, we think what phase? Liquid, but it doesn't mean it has to be a liquid. You could have a solution in the solid, liquid, or gas phase. That includes the air that we breathe. All right, are gases mostly empty space or packed particles? Empty space, yeah, empty space. I mean, we're breathing gases, right? We'd hope it's empty space. Sometimes when it's really humid out, like really humid, there's a lot of water, gaseous water particles in the air, and it feels like you're swimming through Jell-O. All right, that's when those particles might be a little bit more packed than typical, but yeah, typically when we think of gases, it's empty space. All right, rigid or easily compressed? Easily compressed, great. Limited motion or unrestricted motion? Unrestricted, very good, okay, very good. Thinking like if we have, this is kind of like a appetizer to what's to come, but like if I spray some perfume in the corner, right, of the room, eventually everyone's going to smell it because the gases slowly permeate and travel through the room because there's unrestricted motion there. All right, strong attractions or weak attractions against gas particles? You think, what do we think? Weak? Strong? Weak. Yes. Yes, weak. So kind of looking back on these last pieces here, mostly empty space. That means our gas particles close together or far apart? Far apart. So, if we think about our potential energy diagram, right? When things are far apart, D, our distance, goes to infinity, and attractions and repulsions go to 0, right? So there's very little attractions there when particles are very far apart. Okay, particulate level diagram of gases. So here in this container, I have liquid water. Water is H2O. Let's say I conduct some type of phase change to this water. I turn that liquid into a gas. What does that H2O gas look like on the particulate level, right? So what would this diagram be? Right here we see water molecules, so H2O, right? H2O, or if we draw the Lewis structure of water, it looks like that. And so you see those cute little water molecules in there close together because they're a liquid. What would it look like in the gas phase? What do we think? A, B, C, or D? C. C, very good. Very good. Yes, it is C. So my guiding question here, so some of you might have gotten it very, very quickly, but really the key idea that I kind of brought up here was I said phase change, right? Phase change versus chemical change. This is not a chemical change. Chemical change means that we change the identity of the thing. We change H2O into something else. But in this example, we are just conducting a phase change of water, going from a liquid to a gas. So all we're doing is changing how far apart those water molecules are from one another. It's still water. It's just in a different phase. And so it would be C in this case, all right? Because all these other ones, A, B, D, those are chemical changes. So we see that? We see that on the particulate level? Okay, great. Let's keep going. All right. So here's some notes. So when we think about gases, we already mentioned some of these. Some of the elements are gases at room temperature. Our periodic table kind of tells us some of them. The ones that are highlighted red here on these periodic tables are gases at room temperature, but some of them are diatomic, all right? So like all of the noble gases, those elements exist as atoms in their most stable state, but our halogens, nitrogen and oxygens, those ones all exist as diatomic molecules, and we already knew that, right? We already knew that. But they are all gases at, I like to say, typical temperatures and pressures. I mean earthly temperatures and pressures, because really, when we think about, solids, liquids, and gases, most of the time we're thinking of what is the physical state of a substance on Earth, at a typical temperature, like room temperature or whatever. When we think about whether something's a solid, liquid, or gas, those states of matter for different elements and substances may change if we're on a different planet. It'll totally change if we're on a different planet because they typically have different pressures involved on different planets. So you have to kind of think of that balance here. So on Earth, these are the substances that are gases, our halogens and some of our diatomics. Also, we talked about a lot of different molecular compounds in naming them and their Lewis structures here. A lot of those very lightweight molecular compounds, or covalent compounds, are also gases, mainly because they're lightweight. And what we'll see here is because when we have really light molecules, there's not much attractions between different molecules. So when there's weak attractions between molecules, they tend to be far apart from one another since they're not attracted, thus typically being gases at room temperature. So the idea here is if you look at a substance, if it, you would name it as a molecular compound. If this was like chapter 2 naming, it's probably most likely going to be a gas at room temperature. All right, okay, let's squash some more misconceptions. All right, so I got a balloon and I fill it up with helium. All right, we've seen helium balloons, right? All right, so if I fill up that balloon on the left with helium, how does the volume change? The volume of the balloon, does it increase, decrease, does it go unchanged? It increases. Okay, good, don't think about it too much. Yes, it increases. You fill up the helium balloon, you go to the Party City, they fill it up, the balloon gets bigger, right? And then you can see the lovely face that's on the balloon. Okay. What about mass? What if we do the same thing? What if we fill up a helium balloon, all right? fill up an empty balloon with helium particles, like from our helium canister, how does the mass change? Does it increase, does it decrease, or does it stay the same? What? Increase, decrease. Maybe I can't hear. I'm getting older, so I can't hear very well. How about you just point, all right? Let's point. Increase or decrease. We fill up the balloon with helium. Increase. Wow, I see a lot of increases. Or I scared the decrease people. All right, so this was supposed to be a trick question, but maybe you guys are just so smart. I do hope so, yes, that the mass of the balloon does increase. Maybe I gave you the tip where I said, you fill the balloon with helium particles, right? But, you know, we're humans, right? We understand when you fill a balloon with helium and you hold it, what does it do? It floats. So, like, another student would say, oh, no, it decreases because it floats. Do you see that connection there? But that's wrong. That's wrong, okay? That's based upon a misconception here that density is the same thing as mass, but it's not. So the reason a helium balloon floats is because it's less dense than air. All right, just like, you know, a cork floats on water because it's less dense than water, it's the same idea that a helium balloon floats because it's less dense than air. But because we are filling up a balloon with helium particles, one, its volume increases. You know for a fact there's helium inside that balloon, so the mass has to go up, right? We're adding more gas particles inside. But our intuition thinks because a balloon floats, the mass, you know, decreases or something to that regard. But no. Helium atoms do, in fact, have mass to them, so the mass does increase. So that's kind of like a misconception, and I don't want you to fall for it. What did the volume? Oh, it increased. All right, okay, good. All right, so mass, basically the whole idea here is mass is not the same as density of a gas. When we think about gases, they're different. They have different units, right? Mass is grams, density is grams per. When we talk about gases, we'll learn that it's grams per liter because you need a lot of gas particles to weigh to actually get an accurate type of measurement here. Okay, so properties of a gas, how we measure gases in terms of pressure. This is how we measure them about gases and how much we have. Typically, we measure it in terms of pressure. So here, just the unit or the definition of pressure of anything is a force per area. All right. Oftentimes we talk about units regarding pressure. Typically we talk about ATMs or atmospheric pressure. So again, you know, as humans, we're very selfish. Okay. So we name a pressure unit after our earthly conditions. And that's kind of reference, we use that as a reference to everything else. So 1 atmosphere is the pressure that you would feel at 1 or at 0 feet, like at sea level, all right, on Earth. That's the pressure that you feel. So where is this pressure coming from? If we took, what pressure is right, there's air particles, right? Air, nitrogen, oxygen in our air. If we took a column of air, all right, above my head, and collected every single oxygen particle, every particle of gas above my head, that whole column, a square inch above my head all the way to outer space. If we collected all of those gas particles and weighed them, it would weigh about 14.7 pounds. All right, that's how much gas is sitting on every square inch of my head and on your head. That's how much gas is pushing down on us. That's where that pressure is coming from all the air that's in our atmosphere. All right, so that's where the force per area comes from. Force meaning, what's the unit of force? What? Newton meters, yeah, so it's, what's the equation for force again? Work times the distance. That's okay, yeah, I'm not a physicist, all right? So we have a mass being pulled down by gravity, And that's where that force is coming from, and then the area above our head. So we got the mass of all of those particles being pulled down by gravity on a certain area of our head. That's where pressure comes from. And so some different units of pressure. 1 atmosphere is what we basically call like our earthly conditions. 1 atmosphere is the pressure typically exerted on Earth, though it does fluctuate a little bit. All right, day to day, hour by hour, minute by minute. When we talk about, when you like watch the Weather Channel, and oh, they don't have a channel for that anymore, do they? No, it's like just a weather segment on the local news. They used to have a weather channel. Okay, now my age is showing. When they talk about weather, okay, weather patterns, sometimes they'll be like, oh, we're in a high pressure system. All right, and that's exactly what that means. It means that the atmospheric pressure above our heads, that there's a little bit more particles above our heads, so the measured pressure of the atmosphere is somewhere a little bit more than 760 millimeters of mercury or torr. But the weird thing is at least in America, or at least when I look on my phone, and use like the Apple weather app, it doesn't use the unit millimeters of mercury, because that's exactly what that means. Millimeters of like a measurement of mercury is where the pressure reading comes from. But on my phone, at least in America, it's instead of millimeters of mercury, it says inches of mercury, which is, I think, is stupid. I don't know that pressure as well as I do millimeters of mercury, but again, that is a pressure unit. You can look it up on your devices as well. It says inches of mercury, but that is a pressure reading, okay? And so when we're in high pressure systems, it means that we just have a little bit more than 1 atmosphere of pressure in that localized area. If we're in a low pressure system, it just means the opposite. We're a little bit lower than 1 atm. So that's millimeters of mercury and torr. There's our conversion there. Oh, I should note here that 1 atm, it's I should just say that's an exact number. All of these are pretty much exact numbers in terms of sig figs. Sometimes you'll see the unit of Pascal. Pascal, or PA, so Pascal, this is Pascal, is the SI unit for pressure, because it uses kilograms, meters, and all those stuff, so it's the SI unit. So it's a really weird number. It's 101,325. It's like a really weird number. Oftentimes you'll see pascals, but it'll be denoted as kilopascals. So oftentimes you might see that pressure reading in your daily life, all right? And then PSI here. So PSI stands for pounds per square inch, and that's exactly where that whole thing comes from. It's pounds per pounds meaning a mass of some sort or a weight around a certain area, in this case a square inch. All right, so those conversions, memorize those, and you can see, putting them all together, we can use them as conversion factors for any conversion, pressure conversion we want to do. So let's do these conversions really quick, and then I will tell you my joke, my pressure joke. Okay, so we have a gas, and it exerts 785 torr. What is this pressure in atm? So again, brush off your calculator. Identify what conversion we need to use, all right? We want to go from torr to atm. So torr to atm. So the equality I'm going to use is 1 atm equals 760 torr. All right, and I will start with the number that's given here, so 785 torr. And then multiply by that equality I just came up with. And where, with our equality that I have, 600 or 760 is going to go where? Top or bottom? Bottom, okay. I just want to make sure that you're awake and we remember how to do this. Okay, so 785 torr divided by 760. All right, 785 divided by 760. Okay, so this gas exerts a pressure equal to 1.03 atm, so 3 sig figs. So note that these conversions, they have infinite sig figs. So 760 torr doesn't have 2, it has infinite. So 103 atm. There we go. Okay, so if a gas has a pressure of 1.2 atm, what is the pressure in kilopascal? So I want the conversion from atm to pascal. So 1 ATM equals that 101,325 number, pascals, and then note here it says kilopascals, so recall the definition of kilo or kilo anything. So in this case, 1,000 pascals is equal to a kilopascal. So I'll just write that. 1 kilopascal, or kilo of anything, is 1,000 pascal. That's something you should already know. Just so happens to be attached to a pressure unit. All right, putting it together. Start with what's given, 1.2 ATM. I will put the 101,325 up top, 1 ATM on bottom, and then the kilopascal part. So 1,000 pascals goes on the bottom here, and 1 kilopascal goes up top there. All right, so then I like to do everything in one line on my calculator. So 1.2 times 101,325 divided by 1,000 equals 120 kilopascals. And so that's with 2 sig figs because 1.2 ATM has 2 sig figs. Okay. Wow, we probably went like 3 or 4 chapters without doing sig figs. So now it makes a comeback. Okay, so. All right, so good with pressure units. Okay, as long as you know those conversions, you'll be good. They're no different than other conversions we've done before. Okay. All right, so pressure, measuring atmospheric pressure. So I told you that like you go to the Weather Channel or whatever, and they can tell you the atmospheric pressure, you know, currently. What is it right now? Oh, I don't have my phone. I wonder. Because sometimes whether we're in a high pressure or low pressure system, you can predict what kind of weather that we're going to have. All right. Usually when there's really big changes in the atmospheric pressure, it means a storm is coming. Okay, so there you go. People will think that you're like I don't know, like a witch or a wizard. If you can like track the atmospheric pressure, all right, and then predict weather patterns, yeah, they'll think that you're a magician. All right, so atmospheric pressure, this is how we actually measure it. Oh, and so in the corner here, you can measure the atmospheric pressure in the balance room, all right, in lab, all right? So it's behind the door in the balance room. There's a device that you can measure the atmospheric pressure. They used to do a lab where they made you measure it. They made you use that device and measure it. I don't know if they still do that. Did you do it? No? Okay, but it's in the balance room and you can measure the pressure in there. But so this is the idea of where we get our unit millimeters of mercury, because this device, a barometer, when we fill it with mercury, this is how we can measure atmospheric pressure. Remember, pressure is just a force per an area. So atmospheres, all right, when we're on Earth and our atmosphere is pushing down on us, or all those particles are pushing down, we can have a kind of apparatus like this, a pool of mercury, where we have this measuring device, all right, which is just a fancy tube that has mercury in it and a vacuum, essentially no gas, no force inside this tube. So when we put this device outside and pressure, our atmospheric pressure pushes down on this pool of mercury, since there's no force on the inside of the tube, it will push mercury inside the tube, all right? And the amount of force from our, the pressure of our Earth will push that like column of mercury up. More pressure means the column will be higher. If there's less pressure, then the column will be lower. So the whole idea of 760 millimeters of mercury is literally they did this to make this device. They let it equilibrate, and they measure how high the column of mercury is to be equal to the atmospheric pressure, and it happens to be 760 millimeters of mercury. So essentially what we're saying is that the force, the weight of the mercury inside the tube is equal, this force is equal to the force of our atmosphere that we're trying to measure. All right, so when we see changes in that column, that means that our atmospheric pressure, there's slight changes away from 1 ATM. So those two forces are equal. What we'll learn here in a little bit is that gases are always trying to equalize their forces with their surroundings. And this is essentially that. And so the question is, why do we use mercury? Right, mercury, we use mercury because one, it's very, very dense. So we need a big force to equalize that of our atmospheric pressure. So if we try to do this with water, all right, the whole idea is that we need that column of water to equal the force of our atmospheric pressure. If we collected that much water, the column would have to be, how high is it? 34 feet high, in order for the weight of the water to equal that of the force exerted by the pressure of our atmosphere. So that's why it's not realistic for us to use water. That's why we use millimeters of mercury, because mercury is so much dense, we just need less liquid to get that force to be equal. All right, so yeah, I mentioned this. Gases, because this is a vacuum, all right, there's no vacuum, meaning that there's no gas inside this bubble. Right here. So we are able to say, hey, the weight, only the weight of the mercury needs to equal the force being exerted by the atmospheric pressure. When we think about gases in general, like a sample, we have a balloon, there's a gas inside of it, it may change its shape or change its volume in order to equalize the pressure, the forces that are being acted on it on the outside of the balloon. So we can think of there's forces in the surroundings. Those forces can come from a lot of different places. It can come from temperature, it can come from external pressure, those types of things. And it wants to equalize, the gas on the inside of the balloon wants to equalize with the force from the surroundings. So this is where a lot of our gas laws come into play, where we make some type of change to the surroundings of the balloon, and the balloon will have to adapt or respond to it so it can equalize that force. Gases always, that's essentially our kinetic molecular theory, that whole idea, and these different observations that we see. All right, so one last idea here for measuring gases. So in our barometer case, we looked at measuring atmospheric pressure, all right, using a barometer. We can use a manometer to measure pressure of a gas sample. But we can still use the same ideas here, that gases are always trying to equalize their force. So we need to think about where the forces are coming from. So a manometer measures pressure exerted by a gas sample. So here we have a gas sample, all right? And then this column thing, this is filled with mercury, all right? Both of these. So if we look at A, this gas is exerting a pressure on that column of mercury. So now let's think about where is the external pressure is coming from. So this is an open end on our manometer over here. So on this part of the mercury, right? This is our external pressure being exerted on it. So let's think about this. Based upon this picture, which pressure value is more? Which is exerting more pressure, more force? The gas sample or atmospheric sample? Think about where those forces are coming from. What substance in this picture, or what thing in this picture is exerting more pressure? External pressure, like our atmosphere, or the gas sample? What do we think? The external pressure, yeah? Yes? Yes. Yes, so that's correct. So if you think about it, it's like, I don't know, like tug of war, right? I don't know. It's just like two people pushing down on a thing, all right? External pressure is pushing down. The gas is pushing down, but which one is winning? The external pressure, right? And so that's exactly it. So in this picture, external pressure is larger. So the external pressure is larger than the pressure of the gas in A. If we want to specifically say what the pressure of the gas is, if we just called this column of mercury H, we would say that the pressure of the gas plus the column of mercury H is equal to the external pressure. So that, in this case, 1 atm, external pressure. Right, in this picture, because you can think, okay, the external pressure is pushing down here, and it's equalizing that of the height of the mercury and the gas sample in that picture. That's how I kind of like to think of it. Like it's pushing down, and to equalize that, it's the height of the mercury manometer column and the gas sample. So it changes for this picture. So the same idea, right? In which picture, or which substance, P gas or P external, which one is winning? The gas, yeah. So in this example, the gas is exerting a larger pressure than the external. It's winning, all right? So there's the gas, all right, there's external. And so if we call this height here H, if we want to come up with an equation to relate these two, the pressure of the gas is equal to the external pressure plus H, whatever that is in that case. And so in this case, we can say the external pressure is 1 atm, whatever. All right, but it doesn't have to be 1 atm in order for all of these equations to work out. So again, you just kind of think, remember, gases are always trying to equalize the pressure that's being exerted on it from its surroundings. So in these examples, it's not always external pressure, 1 atm, being exerted on it. Sometimes it's also a pressure or a force coming from the manometer itself. And so I guess the question down here, which sample exerts a pressure greater than 1 atm? So which one has a P gas of more than 1 atm, A or B? B, yes, B. So here we said that P gas is larger than P external. All right, we said in this picture the gas is winning. If it's like a pushing contest, I don't know, no, not tug of war, because that's the opposite. I don't know. I can't think of an analogy. You know, just two people pushing on something at the same time, one of them has to win, and in this case, it's the gas that's winning. All right, and so its pressure is greater. It's exerting higher force, more force than the sample, where the gas is losing. External pressure is winning. Okay, so keep that idea in your mind, all right? We have relationships. Gases always tend to try to equalize the forces being exerted on it, and this is where our gas laws come to play. I just want to show you some units that you will become accustomed to, okay, in the coming slides where we do a bunch of calculations. So definitely review these units. You've seen all these units before, okay, yeah? But just, you know, humor me and review them in the coming days. Because we'll be using them a lot. So pressure, we already talked about pressure units that we typically work with, ATM, torr, millimeters of mercury. Those ones are going to be the most common. All right, so definitely know those ones, but know the other ones as well. You see those all the time as well. All right. Okay, also we will work with volume of gases. So liters is the most common. Talked about liters before, but also milliliters, so know how to convert between liters and milliliters. We'll talk about moles of gas, all right? So recall what a mole is. It's just a counting number, a number of particles, all right? Moles. That's not how usually I write it like that, or I write it like that, okay? Moles of gas, or N. Typically, we denote it with the letter N. To mean moles of gas. So this is the same moles as we've been talking about in previous chapters. When we talk about a mole of a pure a number or an amount of a pure substance, it's the same moles. And then we'll also talk about temperature of gases, and we will exclusively use the Kelvin temperature in calculations. All right, within this chapter, always use Kelvin temperatures for everything. But do note is that if you go to the store and buy a thermometer, you'll never find a Kelvin thermometer. It's always in Celsius. So even in questions that we give you in this class, they will typically be given in degrees Celsius, but it's just a conversion away to get it to Kelvin. So do recall that the relationship between Kelvin and Celsius is your Kelvin temperature equals your Celsius temperature plus 273.15. Kelvin. All right, so that's how you convert between those. So do know those. And then all of these different units, these different measurements, we are related to one another with the named gas laws that we'll talk about in a minute here. And so one piece of information that you'll see here often is when we talk about gas samples, we will say the pressure and temperature of those samples, but sometimes chemists get lazy and we don't like to write all of those letters and numbers, all right, especially the degree sign. I hate writing the degree sign on Word. So sometimes we'll be lazy and we'll say the gas sample is at STP. which means standard temperature and pressure. So if you see the conditions STP, it automatically means 0 degrees Celsius and 1 ATM. All right, so it's just shorthand because we're all lazy. All right, so if I say STP, in your mind, you should know it means 0 degrees Celsius or 273.15 Kelvin and 1 ATM. All right, okay, so yeah, we don't have time to do the gas laws, so yeah, so I'll just stop right here. I will show you, all right, the different relationships and some demos of how pressure, volume, temperature, how they're all related, okay? All right, so I didn't prepare anything, okay, for midterm 3 for today. I've made too much. So can we just go, I just wrote recitation 11, which is just a midterm review. So can we do that? Can you bring up recitation 11? Okay, and we'll work through it backwards. Okay, we'll do chapter 9 first. Yeah? Because chapter 9 is the hardest. Are people saying stuff? What? Yeah? Okay. All right, chapter 11. Or sorry, recitation 11. Okay, yeah. I just posted it this morning, yeah. Oh, I did have a joke, yeah. All right, okay, yeah. So let me go back to this page, okay. So a Pascal, all right. A Pascal is the SI unit for pressure, but oftentimes we don't see that unit too often. But 1 Pascal means a Newton meter, or sorry, a Newton meter squared. So 1 Pascal equals a Newton, yeah, meter squared. So see how a Newton is a force and a meter squared is an area? Yeah, you see that? Okay, so 1 Pascal is a Newton meter squared. So Einstein, Newton, and Pascal are all in heaven because they're dead, and they're playing hide and seek, okay? So Einstein turns around, starts counting down from 100, and Pascal goes running off to go hide, right, in the infiniteness of heaven. And Newton stays where he is, okay? And he draws a 1 meter square around where he's standing. I don't know if this is a meter. I think this is pretty close to a meter. 1 meter around where he's standing. And then Einstein opens his eyes, turns around, and he goes, Newton, you didn't go hide. You're right there. Why don't you go hide? And he's like, no, you didn't find a Newton. You found a Pascal. Yeah, that's my joke. Okay, there we go. Yeah, so force per area. If you get anything from that, pressure is force per area. Yes. All right, let's go to recitation 9. Okay. I'm not a good joke teller. Okay. So let's start on page, dang it, I didn't put page numbers on these. Oh well. Question 23. All right. I'm going to save the Zoom questions for Zoom. All right, so let's just do other ones that the other classes won't see. All right, so I have a bunch of pictures of molecular orbitals. So we're working through backwards. We're in chapter 9 right now. So thinking back to molecular orbital theory, all right? It's remembering that, okay, molecular orbital theory and valence bond theory are similar in that it considers how orbitals overlap and interact, okay? That for valence bond theory, in order for a covalent bond to be formed, unpaired electrons in orbitals have to overlap in 3-dimensional space. Molecular orbital theory takes it one step further and says, okay, yeah, orbitals have to overlap, but orbitals, those like S's and P's, those are waves, wave functions, okay? That those shapes are dictated by quantum numbers, right? So they're waves. Electrons are waves. So if you overlap 2 waves on 2 different unpaired electrons on 2 different atoms, they can combine in different ways. They can combine constructively. When we have a constructive interaction, what type of bonding is that? Bonding or anti-bonding? Bonding, so there's no star. Versus if the waves interact destructively, essentially their waves are off by a phase, then you get destructive interference, so that is an anti-bonding orbital, so it has a little star next to it. So the whole idea of head-on sigma interactions, side-by-side pi interactions still applies. We just add the idea of, hey, they can be in phase or out of phase interactions, so it can be bonding or anti-bonding. All right, so in this question, I have a bunch of MOs, and we should identify, just based upon their shape, we should be able to identify a couple things. What type of interaction is it? Is it sigma or is it pi? And we can identify, hey, is it bonding or anti-bonding? Is it like a sigma star or a pi star? Okay, and then even further, we should be able to identify, okay, are they between s or p orbitals? We should be able to identify all of those things. So I did A for you. Okay, so we can see, this is my thought process for A. Here's the MO. I know it's a molecular orbital because it's two atoms interacting. I have atom here and an atom here. They're interacting. So the first thing I think of is like, okay, these two atoms, those orbitals are overlapping in what? Kind of like a head-on interaction or side-by-side? Head-on, yes. So it's a sigma something. Then I ask myself, is the electron density between the atoms, so therefore making a bond where they're shared? Remember, they're sharing electrons for a covalent bond, or is it localized away from the bond? It's away. So if it's away, that means that adding electrons here will actually weaken the chemical bond between the two atoms, so therefore it's an anti-bonding orbital, all right? So yeah, there's very little electron density between the two atoms, so yeah, it weakens the bond in the case here, so that's why it's sigma star. And then further, the subscript here, we say between what two atomic orbitals is this interaction? Yes, it's sigma because it's head-on, but what were the original atomic orbitals that made this interaction? P. Do you see the remnants of a p orbital here? All right, if you squint your eyes, you can see around one atom, it has what looks like a p orbital. Because let's try to find the other sigma star in this. Can we find the other sigma star? C, yeah, C is the other sigma star. It's another head-on interaction, but this time it's not between p orbitals, it's between s orbitals. But see how they're kind of similar? Okay, they're kind of similar, where the electron density is away from the atoms themselves, okay, or the bond itself. Just in C, it's between s orbitals, and between A, it's with p orbitals. Okay, and then further on this question, I want you to locate where these are on an MO diagram. All right, so star, anti-bonding orbitals. Are they lower or higher in energy than bonding orbitals? Higher, yes. So if we look for sigma stars, they'll always be higher than their sigma counterparts. So I always like to remember these are my S interactions, these are my P interactions. So this highest one is going to be that sigma star between P orbitals. So that top one's going to be A. Do you see that? Do you see how I place that? Because they're made from p orbitals, all right? And then C is going to be not the lowest one. It's going to be the higher of the two between the S interactions because it's a star, anti-bonding. You right? Yeah? A. It does look hybridized, doesn't it? But when we talk about MO theory, we only concentrate on atomic orbitals. Yeah, all right. Yeah, so there's no hybrids going on with MO theory. Yeah, but the idea of sigma and pi interaction still applies here. Okay, all right. So let's just go through them. B is what type of interaction? Sigma, pi. Sigma between, star or no star? No star, because it's bonding. There's lots of electron density between those atoms. Between what kind of orbitals? S. All right, so where is that orbital? On the very, very bottom, yes, B. So you can see B and C go together. They go together. They're like they're the bonding and anti-bonding, all right? Okay, keep going. D, what type of interaction? Pi. Is it bonding or anti-bonding? Yes, so it's pi star. And then one little bit more piece of information here, subscript P. Can we have a pi subscript S? Never, ever, never. Only unhybridized p orbitals can do pi stuff. All right, so let's locate D, okay? So D is a pi star subscript P. So where is that on this diagram? Do we know? Right, yes, right below A. What was that? D, yes. So which one is it? Is it this one or is it that one? Which one is it? Both? Yeah, that's probably the closest to the right answer. Yes, it is both, or it could be either of them. All right, so this implies, since there's two orbitals here, two MOs at that energy level for D, it can be either one of those. So that implies that there is another missing interaction, right? Another missing interaction that should be the same energy as D. So if we look back here, is there another pi star interaction being depicted here? Where? Which one? F. But that doesn't look like D. Doesn't look anything like D. It's rotated. Yes, we're looking at it at a different orientation. So if we kind of stood above it, it would look like a butterfly. So D and F are the same, just different orientations. Do you see that? Okay, yeah, so that's why we have to have two lines for pi interactions on an MO diagram, right? Because there's two degenerate pi interactions happening. In this case, it's pi star. All right, so this is also a pi star P. So D and F are these highest ones. D and F. Okay, so we got our pi star. Which ones are our pi interactions? Which letters are our pi interactions? H and G, yes. So if we look at D, we see it's like side-by-side overlap, but it's antibonding, so the electron density is away. But within G and H, do you see how it's still pi interactions, but this time they're trying to concentrate the electron density between the atoms. It just so happens to be above and below the internuclear axis, all right? So those two interactions on the side there are pi interactions. And they're the same energy, right? So these are our pi's, subscript P. So this is G and H right there. Right, is that all of them? No, we're missing one. Which one did we not do? E, yes, E, okay, E. Okay, so E, what type of interaction? Pi, sigma, sigma. Okay, is it bonding or anti-bonding? Bonding, because electron density is between the atoms, but then the question is it between what orbitals? Is it a sigma interaction? Between two p orbitals, yes. So note how we have two different sigma interactions. We have sigma s, and it looks like, see how they kind of look similar in that there's electron density here and here? All right, they just happen to be made from different atomic orbitals. And so E goes, it fits in somewhere right there. That's where E goes. All right? Yes? It's not on the internuclear axis, but it's above and below the internuclear axis, but it's still concentrated between the atoms. So contrast this picture, so H, contrast H to D. So see how D, in D, the electron density is still above and below the atoms, but it's away from the atoms themselves. So that's why it's antibonding. But in H, yes, because the reasoning here is because p orbitals are shaped like dumbbells, all right, and that there's a node actually at the atom, the nuclei themselves, and so that's why you don't see electron density between the two atoms. It's above and below. Okay, all right. So that was pretty comprehensive, all right? But that's what I want you to be thinking about with looking at orbitals. Okay, so let's keep going. Let's do 21. According to MO theory, let's rank these carbon substances by increasing bond length. Increasing bond length. So remember, you are given these diagrams. You just need to know how to use them. All right, and so the whole idea is that both of these diagrams are talking about the S and the P interactions between these diatomic molecules. So really what you need to be thinking about is the number of valence electrons for each of these diatomics. So I give you a series, but the trick here is you always start with the neutral diatomic, then add or subtract electrons as needed to make those cations or anions. But within here, let's think about what the question's actually asking. Increasing bond length, right? It wants us to rank these in increasing bond length. So typically when we're thinking about MO theory, we're calculating bond order, pretty much always, all right? We're calculating bond order. So thinking about bond order and how it trends, when bond order increases, we typically see strength of a bond, what? Increase. A single bond, double bond, triple bond, strength increases. But then when we think about length, length decreases. A triple bond is much, much shorter than a single bond, okay? So we are looking for length, so note how bond order will trend here. So we essentially need to calculate bond order for all these things. Great. All right, so we start with carbon, neutral. So if we write a carbon atom's valence electrons, 2s2, 2p2, one carbon atom has 4 valence electrons, all right? So if I have 2 carbon atoms, how many valence electrons do I place? 8, yes. So I do 1, 2, I'll do a different color. Okay, 1, 2, 3, 4, 5, 6, 7, 8. All right, so do note here what's bonding and what's anti-bonding. Anything that's kind of like the higher one is anti-bonding. So this orbital is anti-bonding, and then these 3 orbitals are anti-bonding too. So when we calculate bond order, we always do bonding electrons minus anti-bonding electrons over 2. Okay, so there's a bunch of ways to do it. I just see that these electrons cancel each other out, so I ignore them. So I just see, okay, there's 4 bonding electrons in pi orbitals here, so the bond order is 2, yes. So the bond order for the neutral molecule is 2, so C2 is 2, okay. All right, so that's the neutral molecule. So if we want to make the cation, what do we do to this MO? If we want to make the cation, do we add electrons or remove electrons? Remove. So you literally just erase 2 electrons. What electrons do you erase? The highest ones. So you go 1, 2. So now what is the bond order? 1. Now the bond order is 1 because we removed 2 bonding electrons. Does everyone see what I did? Yeah. So the neutral one's the hardest, and then once you make the cations or anions, I feel like it gets easier. Right, so C2, 2 plus, we just said is a bond order of 1. Okay. Okay, all right, so let me put those electrons back. Now we want to make the 2 plus anion. So what do to the neutral molecule? Add 2 electrons. So we add them to the next available spot. That just so happens to be another bonding orbital. All right, so if we added electrons to an anti-bonding orbital, it would actually weaken the bond. But in this case, we strengthen the bond, because now what is the bond order? 3, it's 3. So do note, it's not just when you add or remove electrons, you need to be cognizant of what orbitals you're adding them to, right? To calculate bond order. So the anion in this case is a bond order of 3. So if we want to order these in length, increasing length, which one is the shortest? The neutral, the cation, or the anion? The anion is the shortest. Okay, and then the longest would be the cation. All right, and then the neutral one would be in the middle. All right, so C2, 2 minus, C2, 2 plus. All right, so there we go. I have 2 minutes. Is there one that you want to do right now? Let's do the Born-Haber one. Okay, let's do number 7. All right, so here's the Born-Haber cycle. So I give you the numbers. All right? So which step represents the standard enthalpy of formation of the solid? See, the beauty is that all Born-Haber cycles, they're built the exact same way. The formation of the solid ionic salt is always the step This first step, this one right here, okay, the one in the bottom corner, the one that's pointing down, that is our delta H of formation. So that is step 1, delta H1, okay? Which step represents the second ionization energy of calcium? Do we know which one? The second ionization energy. So you might be looking at step 4. Step 4, we remove the first electron off of calcium. Do you see that we form the calcium plus? Right, so the second ionization of calcium will be delta H5. That's where we take the second. We're forming calcium 2 plus in this case. So that step 5 is our second ionization. All right, which, we'll just skip that one. Let's calculate the lattice energy for this, this process. So which, okay, I guess, lattice energy is always typically the step that's on the rightmost side here. There's a couple ways to do it. If you are just good at geometry and can figure out like, okay, given all these different lengths, what does the length of lattice energy have to be for everything to be equal? Lattice energy is typically reported as a positive number. Another way to do it is just using Hess's law. Typically, we kind of ground ourselves in delta H, that first one, the delta H of formation, equals all of these steps. Delta H2, 3, 4, 5, 6. You add all of those up, but you have to subtract lattice energy at the end. So let me set that up. Delta H1 equals delta H2 plus 3 plus 4 plus 5, delta H5, plus delta H6, but then you have to subtract that lattice energy. So we have numbers for every single one of these things. So put in the number that's actually listed there for all those delta H's and calculate for lattice energy, and you should get the right answer. And I think the answer, if you want to do it on your own, is equal to 2,252 kilojoules per mole. I think the key is already posted, so yeah, it's on there. So there you go. All right, I'll see you guys tonight, and we'll do more practice problems on Wednesday. What's up? Yeah.
I was at the review on Sunday with Dr. Chap.
Yeah.
And there were a couple of questions on the test that were like stuff from, I think like chapter 5 or 6, like math stuff. And she told us in the past, the department had like on the third midterm, there was
no, it's no. So if you look at my key, I don't know if you noticed, but that document she provided is one of the midterm side. And so on my key, I specifically say this is not a learning objective for this midterm. Yes.